Here's an example of employing the ratio test to test this series right here for convergence. So of course we have the factorial, and a factorial is a good sign of when you're going to be using the ratio test. There's other cases too, of course, but factorial is a common one to employ the ratio test with. So your a n plus 1, the next term, you got to be really careful about this. The n is replaced by n plus 1. So you don't say n factorial plus 1, you say n plus 1 quantity factorial, and that's being squared. Then you replace this n, you got to be very careful, with n plus 1 in the parentheses. It's not the same thing as 2n plus 1. So let's not 2n plus 1. It's not that. It ends up being 2n plus 2. Okay? And the an is just the original term of the series. So after you put in that n plus 1 carefully in place of n, then you form your ratio of absolute values, and it's written down here. And then sometimes the absolute values are crucial, sometimes they're not. These are factorials. Those are positive numbers. The n is starting at 1. So that's all positive numbers in there, all positive numbers in here because the factorial is positive. So you don't need the absolute values anymore going to step 2 for this case. So I took the absolute values off. I also inverted the denominator and multiplied by it over here. So it's just multiplication of fractions. Okay, then I knew that I was going to have to cancel out with one of these n factorials. So I took the n plus 1 factorial right here, and I burned off one of the factors here, because n plus 1 factorial equals n plus 1 times n minus 1 dot 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 all the way down to 1. That's what n plus 1. So I took the n plus 1 and I wrote this as n factorial, and that's how I got n plus 1 times n factorial. And that's being squared. Then here, I just distributed the 2n to here, algebraically, because I am looking ahead to canceling out with this 2n factorial. But it's not quite ready yet. Then I have the square on this product. So I can just come over here. I put the square on both of the factors. That's algebra. I burned off a couple of terms of this factorial. It's 2n plus 2 it starts with. Subtracting 1 from that is only 2n plus 1, going down one integer at a time. And then you're left with the whole remainder, which is 2n factorial. Because you had 2n plus 2, 2n plus 1, 2n plus 0. That's 2n factorial. And then I left this part the way it was. Then I see that I could just cancel out the 2n factorial. Let's do that again right here. 2n factorial, the 2n factorial, the n factorial squared, and the n factorial squared. And I'm left with this. So now at least I got rid of those factorials, which is what the goal is, really. So then I'm down to here. I canceled out the square on this with the 1 power down here and just got a single n plus 1 quantity. Then that canceled out, so I was left with this on the bottom. And then I moved the 2n, distributed n, and got this. Now I'm supposed to be taking the limit of that ratio as n goes to infinity. So I did that here. And this is what it came out to be. As you can see, as n goes to infinity, that 1 and 2 doesn't matter. We use our normal techniques and we'll get 1/4. This is going to go to 1/4. And 1/4 is less than 1, so we're in case 1, where that applies. And so that's the case where the series converges. Now, you might be thinking, converges to what? Well, that's not part of the original question, but we can still answer it. Converges to what? It does not converge to 1/4. No, not 1/4. That was just the limit of the ratios. That's not what this series sum adds up to. It's a completely different thing. We want to know what this sum adds up to. So we use our Riemann sum program. So in Y1, you put in this, and you don't need to end. You're in regular mode. But the x factorial squared, 2x factorial. Now you might be thinking, oh, I'm worried about x being not an integer. But when we run the Riemann program, we're just going to run it with integers the way we set it up, so it'll all work out defined. If you do something wrong later with running this program, it will gripe because it doesn't know what 3/2 factorial, for example, is. So to get the factorial sign in the symbol, you go to the math key, then you arrow across to probability, and go to number 4 on this. This is number 4 for this one. That's your factorial sign, and you enter that in, and that's how you get your factorial. So then you put your series term right there, and suppose you want to run 1 to 10. Now, why is it only 10? Because you're dealing with 10 factorial in there. Your calculator is going to be crunching along for a long time if you try to put in, say, 100 up here. 10 is big, and even on a calculator, 10 might be big. So you'll just have to experiment. So let's say you wanted that 10. Then you'd be, the way I showed you in another video, you'd be going for a left. And so you're over here with this picture. These are left sum picture right here. So you see, to get the full 10 values, you want to have 11. You want to end at 11 and start at 1. But you need 10 steps. Because whatever you do with this, you better make sure that b minus a over n, 11 minus 1 over 10, turns out to be 1. That has to be a 1. Because your delta has to be 1, so that the heights of these rectangles are the actual an values. Okay? So, you run your Riemann program, and not the integral, because the integral, again, well, we'll explain that in a second. So you look at the left answer, and it comes out 0.736. And that's going to be, it probably has some other digits in your case, but mine rounded off to 0.736 when I did it on the equivalent on the computer. Okay, so why run the Riemann program and not the integral program? That is because Riemann only computes left and right. It doesn't do midpoint or Simpson. If it was trying to calculate the midpoint, it would try to calculate, for example, in between 1 and 2, it would be 3/2. It would put 3/2 factorial, and it would stop right there and gripe, because that would be undefined. Factorials are defined on the 0, 1, 2, 3 positive integers plus 0. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1, which is 2, 3 factorial is 3 times 2 times 1, which is 6, and so on. So recapping, we wanted to find out the series sum, and that series sum was right here, 0.736. And if you tried, it'd be interesting to try lower numbers than 10 to see how close you would get to 0.736. And if your calculator is running really slow, if you push this up to 15, you could see how slow it would take, and if you get any more accuracy.